welcome to this week's SF seminar. Today we are excited to have Jacob from Minifast AI. Jacob was previously a PhD student at Milan and a researcher at Google Brain, and his work spans both theoretical and system perspective on efficient deep learning. The title of today's talk is Scaling Context Requires Rethinking Attention. In this talk, Jacob will introduce Power Attention, a new architecture layer that aims to strike a better balance between the in-context state size and the FFN parameter count. Please join me in welcoming Jacob. I'll hand it over to you. Please get started.
Awesome. Thanks so much for the intro, Songlin, and thanks for joining everyone. Today I'm going to talk a little bit about some work that my team and I have completed recently at Manifest AI on scaling context and rethinking attention. So I know everyone here works on linear attention variance and is interested in the space. So I think I can skip a bit of the preamble here and just dive on in. So the question I want to start with is one that I know a lot of people in this community are often asking themselves, which is, why did transformers win? And this is a question without one right answer. I think everyone sort of comes to their own conclusions about this, but I'll give a little bit about what our perspective is as far as why transformers win. We view it as a combination of two factors. One, transformers are GPU friendly, or I should say more GPU friendly than the RNNs that they superseded. And two, the state of transformers gets large. And I'll go into a bit about what I mean by each of these two things. So starting with GPU friendly. So basically, when comparing a classic RNN, the pre-transformer sequence modeling architecture du jour, with transformer, which has an attention layer, you see basically this different structure in terms of the cost breakdown of the different approaches. So classic RNN, you go through one token at a time, and in the end, your flops are going to be proportional to the number of tokens that you see. So T, where T is the sequence length here. For attention, the picture is a little bit different. You break things up so that they are actually processed in parallel. And as a result, you end up doing T squared computation because you're doing some amount of redundant flops. But the computation is structured as a bunch of big matmuls. And the result of this is that even though the classic RNN has fewer flops, classic RNNs are actually much slower in practice. The time is on the y-axis here, so higher is worse. And we can see that the line for attention is ahead of the line for RNN sequence models in terms of like time per token at basically every relevant context length. It is true that the line for recurrent architectures has a slightly better slope. And so in theory, at long enough context lengths, this trend will reverse, but not on context lengths that are sort of like typically trackable. This goes all the way up to 1 million. So for them to cross, it would be well beyond the range where anybody is working these days. So that's the GPU friendly part. Now, the second factor is that the state gets large. So for this, I want to define the state. Here's sort of one way to understand what the structure of any sequence model looks like. It's a function, as a sort of purely functional way of describing it, from parameters and state, and the output is a response. And now both parameters and state we can view as just collections of numbers, perhaps written to a disk somewhere or in RAM. And the really nice thing about this perspective is it provides a nice symmetry. So the parameters, you start with a data set, and then you use GPUs in a process called training, and you end up with a list of numbers that you call the parameters. And for state, it's actually the exact same picture. You start with some data, which we now call the context. You apply computation via GPU in a process that we call inference. And what you get out, again, is a list of numbers. And these two lists of numbers together completely define the properties of the trained architecture. Now, this is sort of a way that is comfortable to describe RNNs, but for transformers, it may be a little bit more surprising that you could describe them this way. But actually, you can. You just have to realize that the state of attention is the KV cache. And while it is true that this means that the attention state size is not fixed, it's sort of a growing state, that's still completely fine. We're always training on finite sequences or inferencing on finite sequences anyway. So we can just call the state of a transformer to be the state of the KV cache at the largest context that you're going to be using this transformer for. So the reason why this breakdown is important is because while parameter scaling is very well understood. Turns out that state scaling, it's way less studied, but it actually works just the same. In fact, I couldn't find a nice, clean scaling law picture like we see above for state scaling. But we do see sort of like these results in, for example, Mamba, where increasing the size of the state tends to improve performance. But I think even just purely from first principles, when you look at the symmetry on the previous slide and think about how, ubiquitous the scaling laws we see are in deep learning, you realize, okay, it's pretty intuitive that probably a larger state is going to translate into better performance. And here's the thing is that transformers have far larger states than classic RNNs. Transformer states are scale with O of L dt, where L is the number of layers, D is the width of the head, and T is the number of time steps, because you have to store for each of the L layers, T different things, one for each time step, of width D in the KV cache. But for LCMs, actually the entire state of a LCM is just LD. That means that the size of an LCM state is as big as a transformer with one item in the KV cache. And if we're training on the context of 1,000 or 10,000, right, you can see in the plot on the left, you end up with several orders of magnitude of gap between the state size of an LSTM and the state size of a transformer. So maybe it shouldn't be surprising from this perspective that transformers are the ones that scale well, that perform much better. Because with LCMs, you're always going to be bottlenecked by this tiny little state, and you're never going to be able to learn well. Now, this set of properties is just one perspective on it. And I think other people have other ideas about why transformers might have one coming at it from different angles. But I like this because it's very simple, very straightforward, and relies only on basic, like sort of fundamental first principles ideas, compute efficiency and state scaling. But this talk is not about thinking attention, right? It's about rethinking attention. So I want to raise the real question that we want to ask here, which is why will transformers lose? Those were the reasons why they're good. Why are they going to be eventually themselves superseded by the architecture that comes next? And our perspective here is that it just comes down to one thing. State gets too large. Specifically, the state gets too large when we train at long contexts. So, given that I just talked about how important state scaling was, what does it mean for the state to get too large, right? And so this is where I want to bring up a different concept here, something that we call the weight state flop ratio. In general, based on the sort of like pictorial representation we saw before, the functional representation, you can divide any calculation done largely into one of two camps, either a weight flop, which means multiplication between a activation and a parameter, or a state flop, which means multiplication between a state element, for example, something in the KV cache, and an activation. And these two types of activations account for these two types of flops account for virtually the entire flop budget of basically every architecture. And why should it be balanced? Well, it should be balanced because in general, we see log linear scaling across all axes of scaling. And if you have way more, for example, weights than you do state, that means you can continue to increase the state size for essentially free in terms of overall flop budget. It'll barely slow you down at all because you're already spending so much of your time on weight flops. But the marginal value of that increase is much larger than spending that increase on the weight side. And so ultimately, if you just follow this process of sort of rebalancing, taking all the free wins you can get, you end up with a state weight flop ratio that is relatively balanced. It's pretty close to 1-to-1. And we ran some experiments here. So there's empirical evidence for this as well. This is 3 transformers. All of them have the exact same tokens per batch, and they also have the exact same flops per token. So these are fair in every way. They're basically the same scale. However, they have different weight state flop ratios. The lightest line here has a weight state flop ratio of 1-to-12 because it's a very tiny model in terms of parameters, but has a very long context, meaning there's a huge amount of flops spent on the attention calculation in each layer. The line on the bottom, the darkest line, is going to have the reverse ratio, 99-to-1. So it has a ton of parameters, but is being trained on a very short context. But again, the total number of flops between these 3 are the same. And we see sort of a Goldilocks effect, right? The weight state flop ratio that performs the best is the one that's closest to 1-to-1. That's that medium colored blue line on the bottom. And if we plot the weight state flop ratio for a variety of different architecture scales, so we see on the different darknesses of line, different numbers of parameters, and all of the different dots on a given line represent different context lengths for that architecture. We see a really interesting picture. The LSTM, you'll note, is way off to the left. It's completely imbalanced at basically every context length and model size. Transformers, the picture's a bit different. There's a region here in the middle where the standard attention-based transformers are balanced. And what's interesting is that the context length that this corresponds to are exactly the ones where people typically spend most of their budget training transformers. Contexts like 2K, 4K, 8K, 16K, these are all relatively balanced. But when we're thinking about long context training, we're thinking about 128K, a million token context, 10 million, we're way off over here in a way less balanced regime. And the longer you make the context, the worse this imbalance becomes. So the first sort of like obvious thing that we could do to try to fix this balance is something that indeed lots of people do, is to use something like sliding window attention. So if you want to spend less flops on attention, it's simple, right? Just attend over less things. And because the sliding window attention sort of like compounds with many layers, even with a much shorter sliding window than the whole sequence, you can still use attention that is impacted at the end, like but the last layer, the final predictions will be impacted by tokens across the entire sequence. So this seems like a nice solution, but it performs very badly. At equivalent state sizes, if you spend that state on a sliding window of a particular size, as compared to if you spend it on just regular linear attention, there's a couple of variants here, Rokov, GLA, GSA. All these experiments are run, by the way, from the FLA codebase, which makes it really easy to do these sweeps across architectures. You find that it's a very consistent trend. All of the sort of linear attention-based architectures outperform the equivalently sized state and parameter windowed-based architectures. So why is this? We can actually get a little more insight into where this gap comes from and something that makes it feel more like a fundamental issue than just sort of a coincidence of the setting. And to do that, we're going to look at what we call the in-context learning curve on negative log likelihood. So this curve, this one's taken from Llama 4. It's basically just a particular visualization of a model at a particular point. Rather than summarizing the loss into a single number, the average loss, what we're doing is looking at losses at different sequence positions. So we're basically seeing, as you show the model more tokens at inference time, how does its ability to predict the next token improve? And in this case, we see that sort of for the first half of the curve, each additional token is being used, is helpful in predicting the next token. But sort of towards the end, it kind of flattens out and gets relatively little benefit. So this curve here shows the same thing for the process of training an attention model. The different darknesses of the lines are the different updates. So you can see how the in-context learning abilities evolve over time. And we see that basically the more you train it, the nicer and steeper this in-context learning curve becomes. It eventually is able to use the entirety of the context from beginning to end to improve its predictions. But for windowed attention, the picture looks very different. There's this obvious knee here in the middle, where essentially at this point, continuing to show more tokens to the model no longer improves its ability to predict. It just stagnates. It's on average just as good at predicting the next token, no matter what. And you might think, oh, well, this is because it fell out of the window, right? But it turns out this happens well before it reaches the end of the effective context length. It is after the end of the actual window size per layer, but using effective context as a metric seems to really not translate into performance. But this is completely different for an RNN model. The Rokov, this I believe is a Rokov plot, but GLA, GSA, these models have in-context learning curve that look way more similar to attention. In other words, these models can actually utilize the entire state. So it's sort of maybe like obvious in retrospect, but the big advantage that RNN type models have over windowed attention type models is that they're actually able to use information from the entire context rather than just some small recent window. Now, windowed transformer is not the only way to improve the balance of the transform. We can sort of get a really general picture of all the ways you could reduce the size of a KV cache by writing out the shape of a KV cache, right? There's going to be one at each layer, and then by time, and then by heads, and then by features. What we've looked at so far, windowed attention, can be understood as a technique for shrinking this second dimension, the time dimension. The smaller the window you have, the smaller this dimension of the KV cache is. But you can shrink the other things too. For example, hybrid models, where you use a big fat attention layer only 1/8 of the time, and you use a much smaller stated linear attention layer the other 7/8 of the time. These are equivalent to reducing the size of the KV cache by shrinking along the layer dimension. GQA, where you have multiple queries sharing the same key value head, is a way of shrinking the KV cache along the heads axis. And finally, DeepSeek's latent attention, where you, rather than storing the full feature set in the KV cache, store some low rank representation of it, is basically a way of shrinking that final dimension. So what if we don't just use window attention? What if we use some combination of other things? Now, I haven't actually tested all of the combinations of these things, but our initial findings are largely negative. It sort of doesn't matter which way, which technique you use to shrink the size of the KV cache. All these algorithms perform relatively similarly and perform worse than just using an RNN. So this is great news if you're into RNNs, like I assume everyone in this group is. So now all that's left is to find an RNN that fixes the issues with the first generation of RNNs, LSTMs and RNNs, as compared to transformers. So when we think about the advantages of transformers I discussed earlier, well, they're GPU friendly and they have a large state. All that's left is to find an RNN that has these properties. So that's what I'm going to describe now. And that's what basically we have been working on at Manifest AI in developing power attention. So we'll start with the GPU friendly property. This, I think, is going to be familiar to a lot of people in this group. This research was new maybe like a year or two ago, and now it's ubiquitous. But basically, if we take the same picture we had before, we could add a third category of architecture, what I would call a modern RNN, typically based on linear attention. And this family of architectures is sort of interpolation between classic RNN style recurrence and sort of an attention style operation. What it does is it divides the sequence into chunks. And within any given chunk, here the chunks are given of size C. Within any given chunk, we parallelize and do some redundant flops, which means the overall flop cost is proportional to T times the chunk size. But in between chunks, we're just using regular recurrent calculation. So it actually does not grow with T squared overall, it just grows with TC. And the benefit of doing this is that you can use GPU-friendly big matmuls to do the calculation. So what does it look like to actually have an architecture that has this property that you can implement a chunked variant of its computation? The first step is to go from attention, whose formula is given above, although I'm ignoring the denominator and some other details, to what we call linear attention. So you can see it just involves removing the exponentiation on the QKT and replacing it by projection applied individually to both the Q and the K. And what does this do? It allows us to rearrange the computation into an equivalent recurrent form given on the bottom. The algebra here is actually pretty straightforward, so I'm not going to include it here. It's in our paper and a lot of other places on the internet if you are interested. But the upshot here is if you have something that has both an attention form and a recurrent form, it also has what we would call a chunkwise form. You can basically write a different recurrence, a recurrence that involves operations on whole chunks of values and whole chunks of keys, where the thing that is accrued by the state captures the influence of any given past token on the future. An operation which we call querying the state basically captures the influence on any given chunk from the past, from everything that came before the chunk. And within the chunk, we just use regular QKV attention in order to get the local impact. And this is mathematically equivalent to both the attention form and the recurrent form. All three of these are mathematically equivalent, but this one is the most computationally convenient. This is the one that is very GPU friendly. And we can see here that not only does the chunked algorithm have the same slope as recurrent, so it has the nice asymptotic properties that we want, but it also is just strictly faster than attention at all context lengths. So these chunked algorithms are the ones that we really want to be using. All right, so we found an RNN that's GPU friendly. It's linear attention. But what about the state size? It also needs to have a large state. So as I said before, sliding windowed attention is a technique for shrinking a KV cache. So now we're focused on the reverse. Instead, we need to focus on how to enlarge our RNN's state. And the formulation for linear attention that I gave actually has a very natural tool for doing this, this embedding function phi. When we go from a small d to a big D, we call it a state expansion typically, because you're taking a smaller state and expanding it to be larger. So basically, The technique I'm about to show you involves a state expansion, but I'm going to take a short detour to get there. And I want to start by just explaining a different calculation that one could do instead of attention. So now we're going to start, as before, with regular exponential attention and go to something that we call power attention. So just replacing the exponentiation with raising that QKT inner product to the power P. And this doesn't immediately seem like it would provide any computational benefit. But it turns out that raising it to a power P can be interpreted as a form of linear attention. And here's how. If you let phi be this function t-pow, the tensor power, which is equivalent to taking the outer product of its input with itself, p times, then you can actually derive this really cool identity. It turns out taking the inner product of q and k and then raising that to the p power is equivalent to first taking the tensor power p times of q and k each by themselves, and then taking the inner product. So it's sort of this homomorphism where it doesn't matter whether you do the inner product or the outer product first. So that's pretty cool. But the upshot of this is you can now use this identity to write power attention as linear attention. And this allows you to get all the nice computational properties that you want that we just described before that linear attention has. The power attention, despite having this like really sort of clean and simple formulation, is actually as fast as other forms of linear attention. And TPOW is actually just the tip of the iceberg. You can find other embeddings besides the tensor power with the same property, the most important of which is what we call the symmetric power. This here is basically a visualization of why the symmetric power is able to, like what symmetry the symmetric power is able to exploit in order to provide a smaller state that captures the exact same mathematical properties. The tensor power here, you can see the terms are symmetric across the diagonal, which means you can remove about half the terms. And actually, the larger the dimensionality is, and also the larger the power is, the more symmetry is available to be exploited. So you can see in the table on the bottom right here, basically the larger your power is, you can get 99% of the state elements removed and still get the exact same mathematical properties. So what we end up with here, just to like recap the last couple minutes, is you can take linear attention and do the particular phi, and what you end up with is power p attention. And because this is now something that has both the recurrent and attention forms, it can be computed chunkwise in O of t flops while also being very GPU friendly. And finally, it has a state size that can be expanded independently of parameters by adjusting p. So the parameter size is essentially arbitrary, and we can make the state as large as we want. And so we have now found an RNN based on power attention that has both of these properties. It's both GPU friendly and has a large state. So let's see how it does. Let's see it in action. The first and sort of like most essential property, the one that we were going for, is to see that power attention does in fact balance the weight state flop ratio. So in this case, this is with p equals 2. And we see that unlike LSTM, which lies way off to the left, or other modern RNNs, like in this case, Mamba, which just lie somewhat off to the left, power attention is an RNN that lies right on the diagonal. And you can actually just basically shift it around however you want by adjusting P. You can put it at any point on this plot. Standard attention, as we said before, crosses the diagonal for a little bit, but then goes very askew. So the only architecture in this picture that actually has a balanced weight state flop ratio at long context is power attention. Next, power attentions in context learning is better than the equivalent windowed attention. So this is basically the same effect that we saw earlier, where when you train a large model in both the windowed attention framework and the power attention framework with matched parameter size, state size, batch size, all that good stuff, you see that the power attention model is actually able to in context learn throughout the entirety of its context at convergence, whereas you see in the green line, the windowed attention once again sort of stops being able to do any in context learning after a certain point in its context. Next, power attention is a nice, well-behaved architecture. It scales with what I would call the conventional axes of scaling, right? More gradient updates, better performance, better in-context learning. More documents per batch, better performance, better in-context learning. Parameter count, better performance, better in-context learning, etc. So all the ways you would want a neural network to scale, you would expect a transformer to scale. Exact same thing seems to be true for power attention up to the scales that we've been able to test. And finally, and this is sort of the star result, is that power attention dominates other architectures on long context training. Here you can see three as a completely controlled experiment. These three models are all trained with all the same architectural components with one difference. We just swap out what goes on in the attention layer. So our base architecture is Rock of 7. We did a little sweep of base architectures that were in the FLA codebase, and Rock of 7 is the one that we found had the strongest performance. So that's the one we went with, but the same thing should be true no matter which base architecture you pick. The native Rock of 7, which uses a linear attention kernel and includes some fancy tricks like a element-wise gating and also a DeltaNet style update, performs way better than transformers at small flops budgets, but eventually loses to them at large enough flops budgets, which is a sort of a classic hallmark of state size scaling. But power attention is not only able to overtake Rock of 7 with its native kernel fairly early on, it's also able to continue to dominate both it and transformers way further into training. Now, I do think that if we trained for enough flops, eventually it would also lose to just the plain attention model. But at the scales we were able to train, we actually weren't able to go far enough to see that occur. You can also see on the right that the same ICL effects that we noticed earlier are present here as well. Rock of architecture, with its very small state, is barely able to do any in-context learning beyond a certain position at this scale. And by increasing the state size with power attention, we're now able to actually do good in-context learning all the way through the context, just like a transformer, while still having a much cheaper training budget in terms of flops per update.
Uh, so,
And
so sorry
sorry,
to interrupt. Can you go back to the previous slide? I have a
yeah,
question. So, what do you mean by Raku 7 plus power and plus attention? Did you use some sort of hybrid model or?
no, it's just a swap of the architectural layer. So you start with the Rock of 7, and you just go to the one part of the code where they say, y equals, I think they call it like wind attention. It's like y equals wind attention of QKV, right? They just like call some attention kernel. And you can replace that with just y equals flash attention of QKV or y equals power attention of QKV. And that was the only swap that was made.
Um, so why did you call it like Raku 7 plus? Why don't you just call it like power attention or just attention?
Because we wanted to emphasize that the important thing that's happening here is just the layer getting swapped. So the fact that the base architecture is Rokov seems relevant for somebody interpreting this result, even though like the important factor here is not the Rokov architecture, but it's just that's what's common between all of them.
Yeah, so you use Raku 7's like an MLP layer, but you replace the Raku layer to power attention or the soft math attention layer, right?
Exactly. Yeah,
Yeah,
exactly.
yeah, I found this naming kind of confusing because I think it was some sort of like hybrid model.
Oh, yeah, sorry. I don't know. Yeah, maybe we could say Rokov 7 substitute power attention. Maybe that would be cleaner. Um, But yeah, it's just we want to isolate the effect of choosing the attention layer from the effect of choosing the model. That's something interesting. Like I don't know, it feels like lots of different, for example, all the different models in FLA, pretty much all of them come with their entire own architectural backbone, and then also as part of that, bring in a new attention layer. And I think it's pretty interesting that, for example, if you take Rakov and plug in attention instead of the sort of like RNN style attention, it actually performs better than the transformer baseline in FLA. It's actually a Rokov, like the Rokov architecture minus its attention layer is a stronger transformer than the actual GPT-2 style transformer. So it's just like I think there's something nice about cleanly distinguishing between the rest of the architecture and the particular way that sort of time mixing layer, right? The way that information from the past is incorporated into the prediction and really just isolating that.
Okay, okay. Thank you for your clarification. But I would also strongly recommend like fixing this naming strategy because it was really confusing to
Yeah.
me.
If you have a suggestion for a different one, I'm completely open to it. This is just something we
Um,
picked. I'm not like beholden
I
to it at
Jacob,
all.
I think we could call it the kernel. I know we've talked a lot about using different replacements in the Rocket Discord for this stuff, but yeah, we just talked about that as like the kernel. So I think you mostly took everything except the kernel and just swapped that out, right?
Yeah. So the thing about the word kernel is we're actually writing CUDA kernels. And the attention is more than just the kernel, right? Like, for example, the power attention like layer is actually, I think, like 7 different kernel calls, because we have to write the attention forward kernel, the attention backward kernel, and actually even those are also not quite kernels, because really what we write is like the SymPow expand matmul fusion kernel, and then we wrap that in a couple other things to turn it into like update state or query state function. So I just feel like the word kernel itself is a little bit overloaded. That's why I feel like maybe just calling it the attention or something, or like the time mixing, or the, I don't know. I don't know what the right word would be.
Yeah, there might not be a perfect pre-designed naming, because like I know you take like the token shift, for example, from Rocco, but like not the actual, maybe we could say the recurrence.
The recurrence, that's a pretty good one. Yeah, I like that. Although then you'd have to be calling attention a recurrence, because attention itself, like classic exponential attention, totally is one option for this things that could be included here, right? So
Yeah, totally.
Yeah, I think you can simply drop Raku 7 plus in the last 2 rows, yeah, indicating, okay, you are using power attention token mixer. Yeah, and you can potentially you can have some explanation in the caption or in the main paper to say, okay, we use most of the component from Raku 7, except that we just change the token mixer layer to power attention or attention. That should
yeah,
be
no, I
making
mean,
more sense to me. Yeah, yeah,
yeah,
because
okay, yeah,
because
I think that makes
yeah,
sense.
I think the current name really reminds me of like the hybrid model. I was when I read this paper, I think like you are using some sort of like one layer Raku 7, one layer power
Yeah,
attention, stuff like that. Yeah, it's
yeah, I see what you mean. Yeah,
Yeah, until we
yeah,
actually talked
I see
about it
what you mean.
online, I also had the same thing where I wasn't sure actually which components were used and which ones were replaced. So
Gotcha.
there's got to be
Yeah,
some way we can do it.
something I think we did poorly in the initial draft was like I kept the captions on the figures very brief and left most of the details of what was actually going on in the body and in the appendix. And our next draft is going to really beef up the captions, because I think people just want to look at the figure and look at the caption and know all the important information without having to go look somewhere else in the paper to figure out what exactly it is. So I think hopefully the next draft will be clearer. And I also do, yeah, I like the suggestion of just removing the Rock of 7 plus and just keeping it as Rock of 7, power, and attention. I'm going to call it like Rock of 7 attention, power attention, exponential attention, something like that.
Sounds good.
Yeah. Cool. Yeah, we're basically done here. Just a couple more plots I wanted to show. One is that we extended this up to larger scale, 1.5 billion parameters in 32K context, and the trends, if anything, grew stronger. We just see that Rock of 7 dominates early on. Both Rock of 7 and Power Tension dominate early on because of the sort of like improved speed per update. But then Power Attention is able to itself dominate Rockov because the improved state size means it's more able to utilize the full context. And the kernels are available online, open source. They're very fast, and soon will be even faster, at least on NVIDIA systems. This is a little plot showing where we're able to sort of like cross over flash attention. This is actually old. This has it crossing over at 16K. Now we cross over at actually about 12K. And soon it will be even lower, potentially lower than 10K, at least on NVIDIA GPUs. And right now, we just have the kernels, or like the kernels and the attention layer on our open source repo. But pretty soon we'll have a nice little model in FLA as well, so people can just download it. We're going to use Zishuan's Fox attention as the sort of like outer architectural components. We found that one was pretty good, and then power attention on the inside. So that'll be in there soon, and then everyone can very easily play with it. And yeah, just a quick shout out to the SF Compute Company, who provided us with a lot of the GPU resources needed to run the experiments for the stuff. And feel free to reach out if anyone has any further questions, or on Discord, you know where to find me.
yeah. If anyone has any question, please feel free to either unmute yourself or just put the question in the chat.
Yes, just for my education, How do you think your architecture stacks against XLSTM, which pursue also similar goals, like broad similar goals?
I think we actually spoke a couple weeks ago with some people on the XLCM team, and I think a lot of the main principles that I described here will apply directly to XLCM as well. So XLCM is an example of this sort of modern RNN, reimagining of the LSTM, but with a parallelizable sort of like forward and backward pass that makes it really GPU friendly. And it, like the other architectures I described, like Mamba, like GLA, all the linear attention variants that are out there right now, with fixed state size, the state size ends up just being way too small for its parameter count. So it has this very poor weight state flop ratio, very imbalanced. And as such, it's never going to be compute optimal at basically any scale. So I think the XLCM approach could benefit by incorporating these ideas of power tension as well.
So, do you envision any synthesis, like a perfect architecture, which would um, collect, the best features from, both of them, XLSTM and your architecture? Is it possible?
Yeah, I think a lot of changes that other people have made are in many ways orthogonal to what we've done with power tension. Because again, power tension is just changing one very central, very core thing, which is the state expansion. And some things are difficult to merge. For example, the Delta Net style update is very complicated to like that kernel is very complicated, and our power attention sort of like fused symmetric power matmul kernels are also very complicated. And so those two ideas, even though conceptually orthogonal, like you can update a power attention expanded state using the delta rule, right? But actually implementing that is going to be extremely, extremely challenging. I know Songlin had mentioned that it was a work in progress some time ago. I'd be curious to hear how that's progressed, actually. We've also looked into it, and it just seems extraordinarily difficult to actually implement. Other work, so like, yeah, other details of power tension, we actually feel like there's still a lot of work to be done. One example is the normalization. So the normalization that we're using is the same normalization that flash attention used. Essentially, you sum the denominator, right? This is like the softmax has an exponentiation in the numerator, and then the normalization term is summing all of the different numerator terms to get the denominator. And this only works, it only stays stable because they're all positive. And since we're using that same normalization, it also, for us, is only stable if all terms are positive, which restricts us to only using even powers. With odd powers, the expansion works, the mammal works, the kernels work, it's all fine, but the training is very unstable. And so something that we definitely want to improve on and, basically like collaborate with other people who have been working on these sorts of things on is finding the right normalization, the one that will unlock stable P1 and P3 power attention, because those are two very useful sizes to be working with. And so, yeah, like, I don't know exactly what XLCM is doing on that front, but it would be cool to maybe like draw some inspiration or some ideas from there and merge in that way.
Okay, so like on the technical side, do you think is it the main difficulties to writing new kernels?
Um, yeah, I think that's probably one of the main challenges. Actually, for our fastest kernels, which these results do not include them yet, these kernels, the results here were all done with Triton kernels, which at least is a bit easier. But for our fastest kernels, we're actually using a completely like bare bones CUDA script with which we even had to basically write our own library in CUDA in order to implement fast CUDA kernels for these things, because they were just they're somewhat complex. So yeah, definitely a big technical barrier in terms of writing the kernels themselves, but there's also a lot of good scientific opportunities that don't require kernel writing, like the normalization stuff I just mentioned does not require kernel writing. Understanding like lolcats or radlad style, how to distill weights that came from an exponential transformer into a power attention model. This is also something that I think is very like important and of great practical relevance that we haven't really pursued ourselves yet, and would be interested to collaborate with other teams on. So I think while the kernels do pose a big technical boundary to changing certain parts of the algorithm in the architecture, there's lots of other parts that still could benefit a lot from collaboration that don't require the same level of kernel engineering.
Is your code released on GitHub?
Yeah, the link here, let me reshare my screen. The link is here. So this is not the code for all the experiments that will be released at some point. It needs a bit of a cleanup, but this is just the code for power attention itself. You can just pip install and swap, like if you're calling like flash attention QKV, you can just swap it for power attention QKV, and it'll just work straight away.
Great, thank you.
So like my understanding is that this power tension still doesn't eliminate the state quality trade-off, right? It's just providing a new point on the curve. And so it's still like, I mean, it's O to the n in sequence length, which is good. But now O to the D to the P in state size, which
Yeah,
is
it's not quite that extreme. That was the little thing I mentioned about SimPal. So like this column is D to the P. This column, which is the one that it actually is this formula here. It's Z plus P minus 1 choose P. So it grows combinatorially, but not exponentially, which is still very fast. But this essentially is just a free choice. The same way that you can choose based on your training budget and problem how many parameters to use for your model, you can also now choose with power attention based on your training budget and problem how much state to use for the model. And it's going to be the exact same macro level picture as what we currently see for parameters. In other words, for very small training budgets, it behooves you to use a fairly small number of parameters because each update is so expensive that if you use too many parameters, you'll exhaust your training budget in just a very small number of updates and never learn anything. And then on the other hand, if you have a very large training budget, it behooves you to choose a large number of parameters because if you basically have a very small number of parameters, you'll saturate them quickly. They won't really be able to learn much more, and you'll have wasted a bunch of the extra training updates that you were then able to do with your giant budget. So you need to balance how many training updates do I do against how much like parameter scale do I have? And that's what ends up with these sort of like optimal scaling curves. And that exact same picture, you can just mirror that for the state. If you have a small training budget, you're going to end up wanting to pick a small state that allows you to do fast updates and so do many updates on your training budget. But if you have a large training budget, you're going to want to pick a large state, maybe a P2, P3, maybe even a P4. And that is so that you can now basically have a very large, like expressive state. And as you train for a long time, make the most of it. Whereas if you had too small of a state, it would quickly get saturated. And so, yeah, one of the really nice findings here is just that, scaling laws truly are ubiquitous. It's just scaling laws in everything. The same dynamic of, well, if your training budget's small, make it small. If your training budget's big, make it big. It just applies everywhere. It applies to updates. It applies to data. It applies to parameters. It applies to state. It applies to context. It applies to batch size. It probably even applies to, bit depth. Like probably if you're doing a very short training run, you want to be training in FP8. But if you're doing a very long training run, you want to be doing the whole thing in FP32. I've never tested that one, but the pattern is so obvious. I'm just sure it's true. It's just the more compute budget you have, the more compute you want to spend on all axes of ways that you could spend compute.
cool. And I think also it's like, if I'm not wrong, it's like less efficient at short sequences, right?
So something that is pretty cool is that it is not. I don't remember if I left this slide in. Maybe I have it at the end. No, I must have removed it. Dang. But so yeah, the state, because we're using a fixed size state, it is going to be for a very small KV cache. Using a fixed size, fairly large state is going to be larger than a KV cache that just contains, for example, 2 elements. But what's beautiful is because it has both chunked and recurrent and attention forms, because of all of these forms available, you're completely free. They're mathematically equivalent. So you're completely free to, at any given time, choose the state representation that is smallest, which means until your KV cache reaches a certain size, just use the KV cache. And once the KV cache is large enough that the state is smaller than the KV cache would have been, then just convert everything into a state, basically like compress the current KV cache into a state, and then you're good. Then you just use the state from then on. So it's always going to have a less than or equal to state compared to a KV cache based algorithm, because if the KV cache is more efficient, use a KV cache.
Cool. Thanks.
That's a question.
Mhm.
Yeah, it's one. I was wondering, like, what's the biggest P that you try in your experiments? And also, I'm curious, like, whether you will see some like potential unstable training if the P is pretty large. Because the larger P you have, that's like so you do more higher power on the Q and K
Yeah.
product. Yeah.
Yeah, we in the attention form, so with just a pure KV cache, have tried up to P equals 8, and actually a little bit even beyond. But of course, at that point, you could just use exponential attention for the same price, right? Essentially, like, you can see how quickly the state size grows. It basically never makes sense to actually use the chunked formulation. So there could be numerical instabilities with the chunked formulation still present at large P, but for there's actually a very like basically if you take for any P, you can use all the same stability tricks as you would use for flash attention for power attention. All you have to do is take the log, like strip off the sign of the input and take its log right at the beginning. And then literally call flash attention on that and put the sign back right at the end. And if the inputs were in log space initially, then after exponentiating, they just get back to regular space. And so then all you have to do is after taking the log, multiply, right? Because the exponentiation just becomes multiplication in log space. Multiply by 4, by 6, by 8, and this actually produces no numerical stability issues. But again, what I'm referring to is just the attention form. And I do think that the chance for numerical stability issues in the chunked form is much higher. So that's something that like we haven't really been able to work on because just for computational reasons, we haven't been able to push much past like P2, occasionally P4, in terms of like actually trying out the chunk algorithm.
Yeah, another question. Yeah, besides the numerical stabilities, like the training is still stable when the P value is large.
Yeah, in the attention form, everything works fine. Yeah, you see really nice, basically like state scaling, although it does tend to taper fairly quickly beyond like P4. But yeah,
Okay.
you basically can see like P2, and then P4 is a little better, and then P6 is a little better, and then P8 is a little better, but with diminishing returns once you get up that large.
I see. I see. Got you. Thank you.
Mhm.
I have a question. Last week we have a talk on higher order attention. Basically, it's the attention of attention. I think the ideas are similar. Do you have any well, my question is that do you have any observation on the rank of the attention matrix when the P is larger? I mean, yeah.
Yeah. Last week's talk was interesting. They're actually going in the opposite direction, right? Normal attention is quadratic in the sequence length because every input interacts with every other input at every single time step. And that work means each input interacts with every pair of other inputs at every time step. So it actually goes up from like t squared to t cubed. But what we're doing is going from t squared down to t. So it's kind of going in opposite directions, both useful in different domains perhaps, but like sort of like, different deviations from the standard formulation. And sorry, what was the second part of your question? I forgot.
I mean the I mean the rank
Oh, the
of
rank. That's right. Yeah. So we have measured this, and essentially, so our architecture uses gating, as is pretty common, I think, for a lot of RNNs. Just like improves performance a little bit, improves stability. We use headwise gating, not element-wise gating, because it's a little easier to write stable kernels for headwise gating. The element-wise gating is much more complex. And basically, like because the gating dramatically decreases the sort of like basically it scales things down towards 0 and makes things approximately low rank from that point on, like approximately rank 0 if you gate to very close to 0. So it turns out that for most of training, basically like once you've seen at least n different KVs, the rank is going to be around N without gating. But because of gating, we actually see the rank consistently dropping to being like sort of near zero or like approximately zero many times. So typically the rank is actually a lot lower than one would expect. These don't appear to be full rank objects. So maybe there are actually more gains to be achieved by using some sort of dynamically sized state or something. But ultimately, I do feel like dynamic approaches are sometimes a little bit challenging and just like to get working, get stable. And it does seem like there are points where the full rank is used. And I think if we made the rank any smaller, then it wouldn't be able to use full rank when it needs it, even though in general, during a lot of training, the rank is actually quite low. So yeah, maybe a future research direction available there.
Okay. Also, another question is that do you have other do you use other metrics other than loss? Maybe you use like a because I don't know whether loss is although maybe the loss is when you have smaller loss, but the expressiveness of the model might not be good. I mean, do you try other metrics other than loss to evaluate the model?
In this work so far, we've mostly just been focused on the loss. I think you can do a lot with the loss. I think people really underrate it, especially when you go into more nuanced metrics of the loss, not just the average loss over the whole thing, but for example, the in-context learning curve, where you're actually looking at the loss at each token, at each point in training, right? This is a much richer sort of like perspective on what the model is doing and what it's learned. When it comes to downstream evals, I do think there's some value there, but personally, I'm from the sort of scaling laws school of thought, where like the point of the scaling laws research is to decrease the loss, right? Like that's what they all do. All the scaling laws, it's just on the loss, and they want to make the loss as low as possible. And the idea is if you decrease the loss, everything else will follow. Not perfectly. All the other things that we care about are not the same as the loss, they're merely correlated to the loss. So you could have one particular model, which despite having a low loss, is in some particular task or on some set of things bad. But when it comes to architecture research, to me, it just is a clear North Star. It's too powerful. It's too useful. Everything else to me feels a bit distracting. I like downstream evals in their proper place, which to me is when you train a model that you think is useful, right? This research is all about the architecture and the way to train a model, the way to translate essentially GPU hours into lowered loss as efficiently as possible. But once you've done that, there's also lots of questions around like what data set do you use and what prompts do you use and all these other decisions. And so when you're actually doing all that work and combining it all to one holistic complete system, for example, maybe you have an autocomplete, then it will make sense to use downstream evals to evaluate.
Okay, thank you.
Hey, Jacob, I wanted to ask, since you brought it up before, about dynamic sizing of the state and kind of your thoughts on how what directions we might be able to go in terms of like dynamically increasing the size, especially over time, since or over sequence, since of course, as you noted, a 1,000 token context doesn't need as much state as like a 1,000,000 token context.
Yeah. One of the directions that I think seems most interesting here is the mixture of experts but applied to states. So honestly, the only time I've ever seen dynamic computation work, actually there's two, that's not true. There's two times I've seen dynamic computation work. Once is mixture of experts, and the other time is in chain of thought reasoning, which can be viewed as a way to dynamically allocate more computation to harder problems via doing just more steps of unrolling. And between those two, I think the one that's well, attention, you're typically using the full cost thing always, right? You're not actually you're allocating your attention, yes, but you're allocating your attention over a bunch of things. You're always using the same amount of compute. It's not okay. I guess a third place would be tokenization. Tokenization is sort of this hard-coded way to make sure that you're spending your compute more in a more balanced way as far as the informational content of the characters rather than the sort of just like number of characters themselves. So there are a few ways, but yeah, related to what you said, I think that there could be something interesting for using mixture of expert style approaches, but applied on the state axis instead. But one little distinction here, I didn't really go into it in my talk, but there is a difference between state elements and state flops. So you could have a state with a ton of sort of space, for example, with these mixture of expert style things, but still way too few flops. And that architecture would still be improved by increasing the number of state flops. So ultimately, like power attention is doing both, right? It's making a larger state and spending more flops per time step on that state. And so this is going to be yet another axis of sort of scaling that we're going to want to balance. You want to make the state really big, and you want to make the state flops really big, the appropriate amount big for your problem setting.
Yeah, so in terms of dynamically growing the state size, talking about mixture of experts, I guess there have been like some recent papers about stuff like that. Like there's that scaling up the state size paper that just came out. And I think I haven't like gotten super deep into it, but they basically use, I think, multiple states and essentially create some kind of like new distribution of the KVs into the additional like kind of pages of state. So yeah, I guess the thing that's interesting to me is that like when you're training symmetric or just even any power attention, you're kind of teaching the model to use that specific power, and it can't really know how to use like a greater power. So we can't just shove in, power 3 after training on power 2. So I guess I was just curious if you have any thoughts on like ways that you think might jive with power attention, but still kind of give the ability for the learned behaviors of the model to apply to a larger state size.
Yeah, interesting. I think generalization in that sense is pretty hard. It's sort of akin to length generalization, where you lose a lot of the properties, the IID properties that would typically make generalization nice or easy on like a data set style generalization. I do think if you wanted to say train a model with power attention, but just randomly during training, IID decide whether any given example is going to be processed with degree 1, degree 2, degree 3, or degree 4, let's say, right? Then I think that would result in a system where at inference time, you could just choose which of the degrees you're going to use, and they would all work for any given sequence because all the parameters are well balanced to be able to use all of them. So I think that would be pretty cool. Would that system then also work well if you put in degree 5? I'm a bit skeptical. Like I kind of don't see how one could expect generalization on that axis. But I mean, yeah, if there were a way to make it work, I think that would be awesome. Because then you could really, like on a per example basis at inference time, configure how much, basically like how much computational effort you wanted to spend on it in a way that you really can't right now via any level.
Yeah, and that gets back to something you were saying earlier, which is kind of a funny tie-in, which is that since you can view everything as the KV cache equivalent, you could actually go back and like rejiggle the state to become power 3, for example, at a certain point. So you could actually go to 4,000 tokens and then decide, oh, time for power 3, 100,000 tokens, time for power 4, etc. So that's kind of an interesting idea.
Except that breaks like time symmetry, which is a property of these architectures that I find really appealing. Basically, like the amount of the type of work that goes on at any given step of the RNN is the same as every other step. And with what you're describing, there would be these sort of like discrete breakpoints where sort of like one sort of computation happens on steps 1 through 1,000, and then a different type of computation happens on step 1,000 through 10,000. Which, I mean, it could still be a good idea. I think it could be an excellent idea, but it's not as elegant in my view.
Yeah, unless you can figure out how to exponentiate power 2.01.
Yeah. We've thought about that a bit too. Something with fractals. I don't know.
Cool, thanks.
I mean, something that's kind of related to this is you could potentially do a sort of curriculum P, like, start with like P equals 1 for the first like 25% of steps, and then like anneal it linearly, like, 2 to 2 or to 3 or whatever. I mean, that seems like that could work. You'd get like fewer total flops to reach the same loss potentially, because, right?
I think it totally would. We've actually played around a good amount with different schedulings, and in the same way that I think everything scales, I also think that everything that scales can be scheduled. So people often schedule like learning rates. That's a classic one. Some people now also schedule batch sizes. Lots of people who are doing long context training essentially schedule context lengths. If you look at how Llama was trained, right? Most of the training happens at 8,000 contexts. This is Llama 3. It's probably different now, but like the first 95% of tokens are seen at 8,000 tokens context. Then 16,000 tokens context for a little bit, then 32,000, et cetera. And so at the very end of training, you're basically doing this schedule where the first part happens at short context, and then towards the end of training, you start to scale it up. And yeah, I bet like any parameters, I bet you could do this with as well. I bet there's even some work of people doing it because it's kind of an obvious idea. But right, you like start off by training a small model, you do a bunch of steps in a small model. Just as it starts to be converging, you add some new parameters freshly initialized and continue training. Now with a larger model, it's more expensive per step, but also has more parameters, so there's more to be learned. I bet this would work. You can maybe add layers halfway through. You could add longer context. You could add more batch. You could add more state. That's just like also to me fits in this broad umbrella of scheduling things. And yeah,
right. And it doesn't break time symmetry either, right? I mean, as long as you treat like the dynamic p-value as a deterministic function of the current token index, then like it should be fine, right?
As long as within any given sequence, P is constant, or if P is non-constant, but that non-constancy is determined by something that is itself time symmetric. Both of those, I think, are completely fine from a time symmetry perspective. It's just when like at a particular time step, something changes, that's when but even that, like, I don't know, I don't think it's a hard rule that can't be violated. It's just something that causes me slight aesthetic discomfort,
Cool.
Sorry, I have a comment on that. Basically, you can also perceive it as like if you would not just use one power, but multiple powers, so multiple states of multiple powers, and add them, then you have something like a Taylor series, and you may arrive with a certain scaling back again at softmax attention. So it's definitely doable to like interpolate between powers.
Yeah, completely. I think that's also a good way to potentially do sort of an interpolation between P1 state and P2 state and P3 state, would be to just include different terms based on different sort of like pieces of the original input. So basically you could expand you could expand part of the input more than others for any given key or query. And yeah, the Taylor series is a really nice connection. And I think there's been a few works in the past that have tried to do the first couple terms of the Taylor series, but they didn't have the sort of like generic high power formulation, and they didn't have the symmetric power either that make it actually tractable. So there's been a little bit of work in this direction, but I think there's a lot of interesting work potentially still available. Something that is kind of odd though, if you actually use P equals 8, typically it'll outperform regular exponential attention. It'll just straight up beat it. So that kind of got me thinking, like maybe the real reason why exponential attention is good is because it incorporates these high power terms. And maybe the actual goodness does not come from that, like the pinnacle of goodness is not exponential attention. It's just attention with a high power term, which corresponds to a very large amount of state scaling. And when you use a Taylor series, right, it's true that you have a P8 term, right, like a x to the 8 term, but it's downweighted by an 8 factorial term. And so on as you go to higher and higher powers, like these factorial scale downweightings become really serious. And so maybe exponential attention is barely even using its 8th power sized state. It's just like almost entirely dependent on lower powers. And maybe this is why actually just directly using P equals 8 power attention is going to be able to outperform exponential attention, because there's no coefficient, there's no downscaling. You're just using this really nicely scaled state straight up.
Yeah, that's a very cool intuition. Maybe you've heard also of the theory of modern Hopfield networks. So that connects basically this to an energy functional in Hopfield energy.
I'm only tangentially familiar, actually. I'm not familiar with the details of that work.
Yeah, maybe like and what else did I want to say? Yeah. So that would then correspond to basically having a very sharp energy functional like having these high powers, which yeah, like might be beneficial. Also, I think what is interesting is that what people typically observe with attention is that it becomes unstable if Q and K are not normalized at some point, or at least QK normalization is a very common thing to add, and that's actually even more like pruning out these higher powers of the softmax. So yeah, I think it's definitely cool. I'm just wondering if it might become unstable at large scales.
Yeah, like we only have been able to test it up to the scales that we have access to, and there have been occasional issues with stability during sort of like the development process, but they've all been resolvable. Like algorithmically, there seems to always be exit hashes for all these stability issues. But yeah, as you keep pushing the power, that might get more and more difficult to find, and it might end up becoming very difficult to stabilize, but we actually haven't encountered many issues so far. Like the P2 formulation specifically, that's the one that is sort of most natural for the current ranges of architectures that people are typically training. And that one is completely stable. Like we've had basically no stability issues with it at all. Scale up the parameters, scale up the context, use it however you would use a normal transformer, and our kernels seem to be robust to numerical stability issues, and the learning properties seem to be fairly well behaved. So yeah. This is like fixing the norm though. Like part of when we tried changing the norm, like we obviously wanted to train P1 and P3 models as well. So we tried changing the norm to a couple different sort of like norming setups, and then we saw stability issues. So this is like, yeah, there definitely needs to be more space, more exploration in the space of algorithms. Like, do you use QK norm? Do you use RMS norm? Do you use layer norm? Do you use group norm? There's just so many things that, yeah, there's just so many things.
Just wanted to say I do actually have it working with group norm right now with the P3 as of yesterday. But the one question I had about stability regarding that is actually, I know that you guys use this Romax kind of equivalent formulation in the kernel in the simpler version. I haven't been able to like look at the really complicated one in detail. But when you're doing the RNN formulation, are you worried about the lack of the equivalent thing to Romax there?
Anything that we are implementing has the equivalent RNN formulation. So there are some things like, for example, if you just pull off the sign and do it separately and put the sign back in later, that's something that doesn't have an equivalent recurrent formulation. So we discard it basically. We haven't been exploring anything in that space. To us, like one of the key reason to do this, like it is, I guess, I think actually I remember discussing this with you like way back. There is something interesting about the fact that just power attention P=8 seems to beat softmax. That by itself is pretty cool. But the real reason why I'm excited about this research area is not for a slightly better KV cache attention. It's for true linear attention, like a O of T based O of T cost architecture that can really be as strong as the transformer or stronger and unlock training on ultra long contexts at a completely tractable cost. So yeah, to me, if it's a normalization scheme that breaks this property of their existing equivalent recurrent form, it doesn't count to me. You know, it's not something that feels like a core piece of the architecture.
Yeah, I'm excited for that too.
Yeah.
Sort of maybe another sort of idea is like, I'm trying to think about how you might combine this with test time training, sort of fast weights kind of approach. Have you thought about that at all? I mean, like, you know, like maybe treat the state tensor as fast weights, and then, right?
The test time training is very, very similar to this whole genre of work, with the one major exception that it violates the time symmetry. So this is another one that I object to on aesthetic grounds, while appreciating in terms of how strong the performance is able to be. Basically, like the update function for test time training intra chunk is regular like attention-based update within any particular chunk. But across chunks, it uses a different update function. One that is essentially taking the gradient of some like specified objective, turning that gradient into or basically applying that gradient update to the fast weights, which is the equivalent to the state that we have here. So both that work and our work is taking a state vector and applying it via a mapmul to a vector in order to produce the output. That's how our state vector gets applied as well. There is an interpretation as fast weights for basically all linear attention. The difference though is that like for us, the chunk size is a completely computational hyperparameter. There is no mathematical impact on what chunk size you choose. But for the test time training work, there very much is. The chunk size is more akin to the batch size of the inner test time training loop. And of course, batch size has a big effect on the overall properties of learning for like gradient descent. And so ultimately, this is what I view as the biggest distinction. And so we're trying to push as far as we can while preserving this really elegant time symmetry that lets you choose the chunk size that's optimal for your hardware without worrying about whether it's optimal for your learning properties.
Yeah, I think it can still be fitted into a test time training framework without like sacrificing like this time symmetry. I mean, ultimately, yeah.
I think test time training is strictly more general. So this can be fit within the test time training framework for sure. It's just the extra generality of test time framework is they also allow you to break the time symmetry. And I don't allow myself to do such things unless absolutely necessary, which so far it hasn't been. So we'll see how long that lasts.
I had a question about positional encoding also. I know currently you're using the per head gating to do that. Did you guys experiment at all with alternative styles like rope and variations on that might work with, it might work especially well with like odd power sim power powers?
Yeah, we tried. So like the decision to use Rakov was reached by doing this sort of like swap in the attention layer style experiment on a whole bunch of different architectures in FLA. So we did like the basic transformer. Okay, what happens if you put in a linear attention kernel? What happens if you put in a power attention kernel? What happens if you put in an attention kernel? We took Rakov, same thing. We took GLA, same thing, right? And after like a few days of this, we basically came to the conclusion that Rakov is the clear overperformer in most situations. So we just go with Rakov. And so that's basically why we ended up using Rakov as the base for the main experiments. It had the best in-context learning properties. It had really nice stable gradients, like a lot of like really good architectural properties whenever, like basically regardless of which attention we swapped in there. And Rakov turns out to not use rope, so we didn't use rope. But other ones of them did. Like for example, Songlin's basic like GPTT style transformer does use rope. And so we did try it on there, and it just had worse in context learning scaling. It had it was just like a slightly worse architecture. So
yeah, the reason I get to it is just because Rakov always uses per channel decays, and we find that's actually a pretty significant contributor to it beneficially. And I know it's hard to do that here because of, you would have to use some kind of complicated strategies. So that's why I was curious if there might be some other positional encoding method that might allow us to reap a little bit of the benefits of stronger positional encoding without requiring so much technical challenge.
Yeah, it'd be cool. I mean, yeah, I spent a good amount of time implementing element-wise decay and trying to get it to be stable, and I just could not. I couldn't get something that both utilized the tensor cores and was reliably stable. I actually spoke with Songlin like a week or two ago at ICML, and apparently there does exist an algorithm in the GLA paper that does this, but it's more complicated than anything I had attempted, and so I'm not actually sure how easy it would be to incorporate that into our existing kernels.
Yeah, she can speak to it more, but the original RWKV kind of 5 and 6 parallelized version was based on her derivation of that in the GLA paper, and it worked pretty good for us, but we never actually ended up trying it enough to try it with training, so I'm not sure it ended up being, our version of it ended up being precise enough. And we've definitely had a lot of precision related headaches with RWKV7, and so I definitely think you're wise to be wary of making sure that's exactly right before you go down that path, because it is challenging to get right. Songlin's like the master of doing it well, but it can be hard.
Yeah. Yeah. I think it's a little too hard for me. It's just like a rabbit hole, you know? Like if you're not completely confident, then yeah. It's hard to escape from sometimes.
Totally.
Okay, do we have further questions?
I guess I wanted to sort of bang on about the test time training bit a bit more, because I'm not sure it has to break the time symmetry, right? I mean, if you use the states tensor as fast weights that are locally refined at inference time without touching like the frozen base model, um, and then after seeing the prompt, you initialize the state from the KV cache, then like, I mean, it works. It's got exact causal order. There's no look ahead.
No, it's if it weren't causally valid, it wouldn't be a sequence model at all, right? I'm not saying that it's breaking causality in any way. It's just the way, like the relationship between any given pair of tokens, like how any given token translates into an update for the prediction of the next token, is one way of looking at it, right? Like when you're within a chunk, all the new information from a previous token is translated to the next token via attention. Like you're doing intra-chunk attention. Each token is attending to the past recent tokens. And that's a very different sort of like relationship between tokens than how those same tokens are related to the tokens in the previous chunk. Because in the previous chunk, it went through this sort of like gradient descent style calculation that produces an update. And the reason for that is basically the gradient descent, generic gradient descent, I should say. Generically, gradient descent does not have a parallelizable update form in the same way that attention does. So they do this sort of thing that's difficult to parallelize across chunks where they weren't going to parallelize anyway. Like the chunk boundaries are essentially the boundaries of parallelization. There's actually some interesting stuff that you can go into along those lines, but first order, that's basically what's going on, right? And because of that, they're forced to, or they're free to do a much more generic update, and they exploit that fact. So within the chunk, they're sort of constrained. They want to process everything inside this chunk in one big matmul. And so they're forced to use, or well, flash attention, I guess, is two big matmuls, but same gist, right? So they're forced to use a way of updating the predictions based on previous tokens that can be expressed as two big matmuls. And what I like is where all of the predictions, regardless of whether they're intra-chunk or cross-chunk, are related to each other in the same way, in a way that could be expressed as two big matmuls if I wanted to. But then I put my chunk boundaries wherever is convenient for the hardware.
Okay, no, that makes sense.
I'm sorry, I haven't like been there for throughout the whole talk, but I'm wondering if you also use a post attention norm, as it's very common for linear RNNs, as you've seen it in RedNet and like from RedNet on, I think in most architectures. Do you use that?
Sorry, which norm?
Like a norm right after the attention or the RNN. Like
So we use the denominator of the softmax style norm, if that's the one that you mean. We're basically just summing up all of the attention scores and dividing by that.
okay, but there's no layer norm layer afterwards.
That is yeah, that's up to Rakov, I guess. You know, like that's something we considered outside of the attention component. So if the original architecture that we're plugging our attention layer, our power attention layer into had a layer norm there, then we have a layer norm in that same place. But the power norm itself doesn't come with a layer norm. It just comes with this sort of like softmax denominator. We call it like a temporal norm because you're summing up the attention scores over time and using that to normalize. So power tension itself only comes with that, but some of the architectures put layer norms or RMS norms in various places, and we kept those.
Okay, thanks.
All right, let's wrap up here. Thank you again to Joe for the great talk and discussion, and thanks everyone for coming. And we'll see you at the next seminar.
Thanks, everyone.